Hello, I'm Kenneth Holmes, and today I would like to talk about action potentials. Let's start by talking about what I mean by potential. When talking about potential, we are discussing a difference in charges. Cells can have membrane potential depending on available ions both in and out of the cell. A neuron or muscle cell can utilize changes in the potential to send signals. For example, a neuron often has a large amount of potassium inside of the cell, compared to what is found outside of the cell. In return, outside of the cell has more sodium than inside the cell. Due to this difference, as well as other ions available, there is a difference in charges across the membrane. At rest, inside of the cell, is found to be about -70 millivolts. While a cell may be at rest, this does not mean that zero action is occurring. Within the membrane of the cell, there are pumps and channels. Leak channels allow for potassium to diffuse across the membrane, leaving the cell until there is enough change within the internal charge that potassium can then diffuse back into the cell. The same occurs with sodium. Sodium will diffuse from outside of the cell into the cell until enough charge change has occurred that the sodium will begin to diffuse back out of the cell. The pumps, however, utilize energy to move sodium and potassium against the gradient. This means that with the help of ATP, sodium is moved out of the cell to a place that has more sodium, and potassium is moved into the cell to a place that has more potassium. Because of this work, it maintains the potential across the membrane. This also means that it aids in the creation of electrochemical flow, meaning as sodium moves out of the cell, that its electrochemical flow is also moving out of the cell. Just like when potassium moves into the cell, the potassium's electrochemical flow is into the cell. This is a way to measure the balance of the overall electrochemical flow into and out of the cell. There are also voltage-gated channels that I will discuss in more details later. Within this image, we can see the leak channels and the sodium-potassium pump. While the leak channels use diffusion, and thus no outside energy, to move the ions into and out of the cell, the pump will use ATP to move 3 sodium ions out and 2 potassium ions in to the cell. This will help maintain the -70 millivolt resting potential. Now let's talk about depolarization and repolarization. Depolarizing is the act of becoming less polarized. In the case of the neuron, whose resting potential is -70 millivolts, it is becoming more positively charged, is losing polarization. This means it is depolarizing. As that charge begins to return to resting potential, it is then repolarizing, meaning that it is gaining that polarization back. If, during the act of repolarization, the cell overshoots and becomes even more polarized than resting potential, it is known as hyperpolarization. Using our neuron, where the resting potential is -70 millivolts, if the cell reaches a charge of -80 millivolts, the cell is then in a state of being hyperpolarized. This generally occurs due to the slow reaction time of the potassium voltage-gated channel closing. Voltage-gated channels are channels that have a reaction to a specific range of charges. For example, at about -55 millivolts, the sodium voltage gated channel will open. This will allow a large amount of sodium to flow into the cell in a normal leak channel. This causes the cell to depolarize. Shortly after the gate opens, a special polypeptide ball blocks the opening to the channel, stopping the flow of sodium into the cell. The channel then closes off. All of this happens in a very short period of time. Here, we can see an image of the sodium voltage gated channel. The first image, on the left, depicts the channel outside of its threshold range to react, making it closed. When the stimulus is provided that changes the polarization of the cell, this causes the channel to open, as seen in the middle image. This allows for the ions to flow in. Soon, the polypeptide ball will begin to block the channel, stopping the flow of ions, as seen on the right. All of this feeding the depolarization of the cell in its surrounding area. When a stimulus is provided that depolarizes the cell to the threshold of -55 millivolts, we see a sodium voltage gated channel open. This allows the sodium to flow into the cell, again depolarizing the area. This, in turn, will cause other sodium voltage gated channels to hit their threshold in the area, causing them to open as well, which in turn will depolarize more of the area, causing more voltage gated channels to open, making a feeding effect that depolarizes the cell. Once the potential in the cell reaches about +30 millivolts, this causes potassium voltage gated channels to react. They will begin to open, allowing potassium to flow out of the cell in larger amounts than the leak channels. This allows the cell to begin the process of repolarization. We can see in this image the stimulus providing enough depolarization to meet the threshold. This allows for that surge of sodium to enter through voltage-gated channels, continuing to depolarize until it reaches about +30 millivolts, when the potassium voltage-gated channels will begin to open. This allows for the flow of potassium out of the cell, allowing it to begin the process of repolarization. The potassium channels take longer to close off than sodium voltage gated channels, leading to hyperpolarization. This hyperpolarization is not a bad thing. Because of this hyperpolarization from the potassium channels, this means that depolarization occurring from nearby sodium voltage gated channels will not cause these sodium voltage gated channels to react. Due to hyperpolarization, the sodium voltage gated channels would require a greater stimulus than the depolarization offered by their neighboring sodium voltage gated channels. This creates a signal that moves in one direction.